Good afternoon, everyone, and thank you for coming to hear me talk about reference materials after a very busy 2 days of accreditation matters. As Paul said, I work with the National Measurement Institute, and hopefully you've learnt quite a bit about our organisation over these past 2 days if you didn't already know us. We had a table in the foyer, and we've had other speakers, including most noticeably our CEO, the Chief Metrologist, giving the keynote address this morning. My area of the National Measurement Institute is chemical and biological measurements, and in particular the chemical reference values section. So I'm going to talk to you about reference materials from the perspective of someone who certifies matrix reference materials for use in chemical testing for organic residues, but you can extend some of these concepts to other materials. So why does accreditation matter to us in certified reference values section? Well, our major activities include production of certified reference materials, for which we're accredited to ISO 17034, the conduct of proficiency testing, for which we're accredited to 17043, and the assignment of reference values, which we do both for some samples for our proficiency testing studies and for external clients according to their requirements. And for that, we're accredited to 17025 for testing and calibration laboratories. And our accreditation matters to us in these circumstances because it matters to our clients. It's part of the chain that allows them to obtain and maintain their successful accreditation. For example, participation in a proficiency testing study conducted by an accredited provider is a very good way of maintaining your accreditation as a testing laboratory. Accreditation also matters to us because it matters to Australia. It facilitates recognition of Australian measurement results internationally. One of NMI's roles is to develop and maintain measurement standards to ensure Australian measurements are traceable to the International System of Units, the SI. The National Measurement Institute sits in the middle of this metrology pyramid. And as we look up, there are the regional metrology organisations. Australia is part of the Asia Pacific Metrology Program, APMP, and there are 6 of these regional metrology organisations. And the International Metrology Organisation, the BIPM, the International Bureau of Weights and Measures, which is based in Paris, and which is the organisation that maintains the International System of Units, the SI. And so at the National Measurement Institute, we participate in international comparison studies, which are like PT studies for national metrology institutes by national metrology institutes. But when we all participate in one of these international comparisons, then once the results are in, all the participants get together and talk about the results, determine what the answer should have been, and if there are any measurement challenges that have been identified through that process that need to be addressed by the international measurement community. And then as a result of participating in those studies, the various organisations can all agree to recognise each other's capabilities for these measurements. Also, NMI maintains our accreditation. That's part of our link to the international measurement system. And when NATA comes and organises to assess us for our accreditation, for a technical assessor, we usually need to organise someone from another national metrology institute so that we can be assessed to a suitable metrological level. And then the Australian testing laboratories maintain their accreditation, use certified reference materials, and participate in proficiency testing studies from accredited providers, and that links them through our national metrology infrastructure to the international metrology infrastructure and ultimately the International System of Units, so that a result from an Australian testing laboratory is then recognised internationally. Some definitions from the International Vocabulary of Metrology, the VIM. A reference material is a material that's sufficiently homogeneous and stable that we can use it to measure a property value with a particular procedure. It has to be homogeneous and stable because we want to prepare that reference material. We want to aliquot it out into units. We want to be able to put those units in the fridge and then send them out to clients when they need them. And we want to know that as long as they have been treated according to suitable storage procedures and suitable transport procedures, that every client who receives that reference material if they measure it with a suitable procedure, they will get the same answer, so hence the homogeneity and the stability. A certified reference material is a homogeneous and stable reference material for which the property value has an assigned uncertainty and a metrological traceability to a stated reference, which is often the SI units. Reference materials and certified reference materials are both components of a successful accreditation. They have slightly different applications. Before I talk about those roles, I just want to share some of what I think is the interesting part of production and preparation of certified reference materials, all the work that goes into making them. So because what I work on is the preparation of matrix certified reference materials, usually what I'm talking about as a property value is a mass fraction, and it will be of an analyte like a pesticide or a drug residue or an environmental contaminant in a biological or an environmental matrix. So in these examples, a tomato puree, for example, or freeze-dried prawn material, or a contaminated soil. NMIA does have a section, my colleagues, who prepare pure substance certified reference materials. So these would be the high purity materials like this pesticide metabolite, endosulfan sulfate, that you would use as calibrators in your analysis. But that's a slightly different issue of preparation and certification. So talking about reference materials, the ideal reference material obviously would be a material that behaves exactly like a real sample in laboratory analysis. But how would we deliver a tomato guaranteed to contain 600 micrograms per kilogram of endosulfan sulfate to every user? Or how would we prepare a sample of prawns guaranteed to contain 10 nanograms per gram of antibiotic residue and distribute those samples across Australia without the prawns going off? Most of the work in the production of the reference material is creating a homogeneous material and finding a way to ensure its stability without compromising the behaviour of that sample in the chemical analysis so that it doesn't look too different to a real sample. So for example, to produce our tomato puree reference material, after we've washed and chopped all these kilos of tomatoes, they have to be pureed and sieved to ensure that we have a homogeneous matrix base. We had to spike in the pesticides of interest at suitable levels and then mix it some more to make sure that they're distributed homogeneously through the material. And we have to dispense it and package it and freeze it. To prepare the MX12 freeze-dried prawn material for nitrofuran antibiotic marker residues, not only do the prawns have to be peeled and blended, but it had to be freeze-dried, and that freeze-drying procedure had to be repeated twice because it was necessary to reduce the moisture level sufficiently that we're confident that we can store and transport that material without unwanted microbiological activity. So that's the process of producing a stable material. If we want to produce a certified reference material, we also have to add metrological traceability to that material. Analytical chemical results are often reported in units like milligrams per kilogram. That's implying a traceability to the SI unit for mass, the kilogram. But if we establish metrological traceability, that makes that link explicit. Now, in the first diagram there, talking about the comparability of results in two laboratories, it's important to note that I'm not talking about comparable as meaning of a similar magnitude. So if I say that laboratory 1 measures 0.001 grams per mil of a pesticide in a sample, and laboratory 2 measures 0.001 ounces per pint, or whatever units they choose to use, in a similar sample, those are not comparable results just because they're the same magnitude. In fact, they're not comparable results at all because they're not in the same units and they're not traceable to the SI. In this example, though, our two laboratories are doing the right thing. They've both used traceable commercial certified reference materials as their calibrators in the middle of those chains. So both of those materials have a suitable traceability chain back up to the international system of units. And then when the laboratories apply their carefully controlled procedures and calculate their uncertainties, they can transfer that traceability to their measurement results, and then they will have a comparable result each traceable to the international system of units. In the second diagram, the second laboratory just used a reference material. They have a purity value and nothing else, so they don't have traceability to the international units. And so those results are not fully comparable. Traceability is not always easy to demonstrate or to report on a certificate. So if you're choosing a calibrator for your analysis, so the pure substance reference material that you want to use to make your standards to determine what your results actually are in your analytical method, you need to inspect that certificate closely and ensure that the traceability statement on that certificate is suitable for your needs. And one of the ways to convince yourself that that statement is suitable is to check the accreditation of the provider of your certified reference material. So now the next stage in producing a certified reference material, assigning that traceable value, is more than just doing a quick analysis. First of all, there was the production of the material to make a suitable, homogeneous, stable material, all bottled out into units. And then to assign a value, we need to develop a high accuracy measurement procedure and validate that procedure. Now, we are only applying this measurement procedure essentially to one sample. It's only to tomato, and it's only got a limited number of analytes in it, in this case 6 pesticides, and they're only at a certain low level near the regulatory limits. So validating the procedure is not like validating a routine method where you need to show that it could be applicable to many different samples, like lots of different fruit and vegetable matrices and hundreds of pesticides at all sorts of levels. But still, we do need to demonstrate the precision and the absence of bias of that method. Once we've developed that method, we might analyse that sample 100 or more times by the time we've demonstrated the absence of bias, got measurements to assign a property value, done homogeneity studies to demonstrate that both within the bottle and between the bottles, all of the samples give the same results, stability studies to show that what conditions we need to store it under, and to show that under reasonable expected transport conditions, our analytes are also stable. And of course, before we can do all of these analyses, we need to source a suitable certified reference material as calibrator for our analytes. So here we have an example of a material that we obtained from our colleagues in NMIA, pure substance certified reference material for endosulfan sulfate. And there were other materials that we obtained from them and from other accredited producers of reference materials for pesticides. When we've got all those values, we have assigned a property value we've assigned property values to our reference material, and then we need to evaluate the uncertainties that go with those. Some of those uncertainties are given to us already on these certificates by our very helpful providers of reference materials, certified reference materials, or the provider who calibrates our balance. Other components we have to take from our measurements of, for example, precision, bias, stability, and homogeneity. We have to combine all of those results using suitable statistical procedures, and then we have a property value and an associated uncertainty. But still, we're not done. We have to prepare a certificate according to the requirements of the standard to which we're accredited, 17034, and also to the guide to the contents of certificates, Guide 31 as was. I think it's now ISO 33401 this year. And some of the things that we have to put on the certificate include storage and transport conditions and any other relevant conditions like conditions for reconstituting a sample, subsampling it, handling it within the laboratory, so that the customer who buys that reference material can have confidence that as long as they follow those instructions, the property values for their material will be maintained at least until the expiration date on the certificate. We also have to put a metrological traceability statement on it, and we have to include enough information on that certificate about the processes that we've used to produce and certify that material that the client can be satisfied that it's suitable for their needs. So that's preparing a material. At the beginning, I talked about why accreditation was important to us. A couple of reasons that we've heard throughout the last 2 days why accreditation would be important to you if you are a laboratory producing testing results. It facilitates recognition of your results by regulatory bodies everywhere, from the traceability that you've got on that result. And it ensures the reliability of your result because of the quality processes that you're following to validate and verify and control your methods and to control the other aspects of your environment. So some examples from where the standard 17025 for calibration and testing laboratories talks about reference materials and certified reference materials as components of accreditation. The big one, obviously, is metrological traceability. And here again is our endosulfan sulfate. If you're going to prepare a calibration curve, you should use a certified pure substance reference material with a suitable traceability, because that traceability will be transferred directly to your results. In evaluation of measurement uncertainty, again, you need your certified pure substance reference material. The uncertainty on that is going to go straight into your uncertainty for your result. But also reference materials can help you with calculating other components of your uncertainty, like the method, method precision and bias. Reference materials and certified reference materials are also discussed in the context of validation and verification of methods and ongoing quality control. Many of these applications are somewhat more suitable for reference materials than certified reference materials, but a certified matrix reference material is a very good tool for determining the bias of your method, if one is available, because these materials are certified usually with tighter uncertainties than you will get from a routine method. So it's a very good tool for determining the accuracy or the recovery of your method. But unfortunately, in the real world, there are many, many more combinations of analytes and matrix found in real samples than we could ever produce certified reference materials, given the amount of time and effort that it takes to produce these. So some of these other tasks, like evaluating the precision of your method or monitoring the results of your method over time, are probably more suitable for other homogeneous and stable materials that are slightly cheaper and easier to obtain. A good example of a material that could be used for some of these applications are samples that have been studied in PT studies. So they've had their homogeneity demonstrated, and there's often stability information available for them. And coincidentally, NMIA has some of them available in our back catalogue if you're interested in those. And I think, hopefully, given that you've all been here for 2 days and enjoying the talks, you're all convinced already that accreditation matters. And hopefully I've shown you that reference materials and certified reference materials are very useful tools and a good investment as components of your successful accreditation.
The first one, I think, is, and it's a very good question, one I hear a lot, is doing assessment activities in the testing laboratories. And it's about fitness for purpose. So the question is, I work in a routine lab, and my customers don't care if I use a CRM as against an RM, so certified values against just reference values. Are there any reasons why I should still consider using a CRM?
Well, I think the answer to that is the traceability, but again, as you say, it's fit for purpose for your customer. But I think the standard does want you to have your traceability of your results, ultimately, doesn't it?
I could refer to that. I could also go to NATA's own policy for metrological traceability. Yes, I would concur that if you wish to claim that your results are comparable with other laboratories around the world, the use of a certified reference material, and particularly that traceability statement that I saw at the end of your certificate there, is very valuable in demonstrating.
And I think if more people wanted to use certified reference materials and we had more funding to produce certified reference materials, they would become cheaper. So perhaps it's a bit of a chicken and egg problem.
If you have any questions from the testing laboratories, please do come see us, myself and my colleagues, at any time. Another very good question here is, how do you determine the expiry date for certified reference materials in the matrix?
That is a very good question. We do stability studies. Usually we have to store them for at least a year to be sure that it's part of why it takes so long to prepare them. 6 months to a year we have to store them to be able to extrapolate the stability of the analytes before we can even think about sending them out the door.
A further question here with regards to what's the most challenging aspect of certified reference material production? Any particular project that was quite challenging and yet fulfilling?
Well, recently we did this tomato material, which we thought people might be excited about because customers of our PT studies have been looking for a material, but I think they're possibly not realising it's available yet. But just to do 6 analytes at once for us in one material with the sort of methods that we do, which are targeted to each analyte, is just a lot of work.
Yeah. Matrix materials are challenging. If a reference material from a partner organisation is used in validating your methods, so I think this is spoken on behalf of the testing laboratory's perspective. If a reference material from a partner organisation is used in validating your methods, how are they referenced back to true values or actual values?
Well, that's a very good question, and it would depend on what the reference material was that you were using. Possibly it's not.
Yeah.
When you have a unstable material such as benzene, how do you make a reference material for something that loses volatiles over time, and does that have a shorter holding time compared to like a sample, for
that's
example?
another problem with reference materials. Sometimes if you haven't got the stability, you haven't got the reference material. You have to find a way. And when you say benzene, you're talking about a pure substance or a...
Yeah, like B-tex is benzene, toluene, ethylbenzene, they're volatile.
Residues of those things, if they're volatile.
Yeah, so we test it in like contaminated land studies.
Yeah.
And generally, yeah, they lose volatile even during transport. And not
Yeah,
cold storage
and I think that would be a whole other issue. We, at our lab, don't work very extensively in that area, so we're not very familiar with how we would stabilise those things. That would be the part that I was talking about in the production, to determine if it's even possible to produce. If you're going to produce a certified reference material and put months and months of work into it, it has to be something that's going to be stable for years.
Yeah.
So some things, you have to think about the problem differently, I think.
Yeah, okay. Okay, thank you.
Any other questions? I've got a question, if I may. Look, the work done by the National Measurement Institute is invaluable in providing certified reference values to the Australian technical infrastructure and all of our accredited reference material producers as well, because I can see some other reference material producers in the audience as well. But that's for Australia. Do you actually have a market, or do you offer certified reference values outside of Australia as well?
Well, theoretically we do. We have, certainly with some materials like this, we have issues with being in Australia and being so far from the rest of the world, even issues with moving biological materials around between. We do reference material work for the sports drug area that are very popular around the world, but that's a slightly different material that's funded by the sports drug work. We try to sell reference materials around the world, but around the world there's a similar raging interest in purchasing expensive materials that that we all understand why we're making, but nobody seems to understand why they should be using.
Yeah.
Or can't afford to use.
Very good answer. Are there any more questions? Well, please join me in thanking Dr. Lesley Johnston once more.
Thank you.